Okay. So based on the introductory remarks I have made, let me start revealing the properties of the rotation operator or rotation matrix. So if we think that if we have a collection of coordinate xi, and if we make a transformation to xi prime via an expression of this, repeated indices are summed. If you want, think of it there as a j. But usually I will suppress, as always, understanding that repeated indices are summed over. You can say there is such a relationship between x1 prime, x2 prime, x3 prime, and the x1, x2, and x3. The requirement that it is a rotation is contained in this relationship. We said space rotations are those which keep the lengths of the vectors fixed. So if I write this, what kind of constraint it imposes on these rotation operators? So we write the left-hand side as x prime squared, which is x squared should be equal to that. Xi and xi, sum over I, is equal to xi prime and xi prime, which is sum over I and rk, xk, and ril, xl. So there is a summation over k and l as well. Okay. So I have written that transformation and set the lengths equal to each other. In the left-hand side, the length of the unprimed vector. In the right-hand side, the length of the primed vector. So if you rewrite this in the following form, rik, ril, xk, and xl, obviously, in order to get the left-hand side, I have to have this as delta KL so that I can carry out the summations over K and L and get the xi and xi as in the left-hand side. That is the equality of the lengths, right? So that gives me the beautiful relationship that these transformations should satisfy. Rik, ril, that is with the sum I coming in here, right? I is already contained in here, so if it becomes delta KL, you can carry out one of the summations. There is a single sum left, which is xk and xk, right? I'm not going through these steps in detail. I understand that these are all well covered in one of your previous linear algebra classes. Okay, so if this is the relationship I obtain from that equality of the lengths. What does it mean? I can rewrite this slightly differently, write it as R transpose K and I. The purpose of this, putting the indices, neighboring indices next to each other to make it a matrix summation, right? Notice that if you write it, change transpose Ki, Ik becomes Ki, so that I's are put next to each other. That's typical matrix summation rule. Then it becomes RT, R sum is taken care of, delta KL, or if I carry this over here, RT, R is the identity. That is, these rotation matrices in space are orthogonal matrices, because that means that R inverse is the same as R transpose in whichever direction you like. Orthogonal matrices. As we are in the tree space presently, these are 3 by 3 orthogonal matrices. And if you were doing it in the plane, 2 by 2, in a two-dimensional space, then they would be 2 by 2 orthogonal matrices. Our job is not to teach you group theory in this class. We are going to use minimum amount of it just to proceed as fast as possible towards physical applications. So I will deviate from the book at this level because semester is running short and I have to speed up a little bit. So he works on further details of these orthogonal groups and the elements of the orthogonal groups. I will instead do an operational method of showing you how to construct explicitly the rotation matrices starting from infinitesimal forms and eventually check that it indeed satisfies these orthogonality properties and really use it that way. Perhaps I have to switch to the left-hand corner as I'm going to keep that picture, the new picture I'm going to plot on the board to refer to every now and then. That is the actual construction of a rotation. Okay. Let me try to do it properly because it's going to be used extensively. So it's difficult to plot such pictures on the board, but I'll try my best. Okay. 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 You can perhaps draw better pictures on your notebook. Here is the rotation axis, so I put n, a unit vector along that line. So I'm really revealing all the properties of the rotation which we have described. Here is the vector x reaching to this point, and here is in the back the x prime vector reaching that point, and this is the amount, this portion which I have defined in delta x, x prime minus x. Okay. And I call this angle alpha. Apparently, if you just go after the rotation, that's going to be alpha again, fixed. If the length is to be fixed, this distance is to be fixed. It should rotate about this axis. That will be what we, the rigid rotation that we are really talking about, right? So what is this distance? Let me look at this triangle, and this is the length x. So this length is x times sine alpha, right? It is this length. And let me call this the angle delta theta. I'm constructing it infinitesimally in the plane, and is the unit vector in this direction. This alpha is the subtending angle of the vector when it's rotating around this axis, keeping that alpha fixed so that this fixed. So I can write now the delta x magnitude in this circle if it is infinitesimal. So this is an infinitesimal arc. Therefore, the length will be delta x will be just this distance, x sine alpha times this angle delta theta. Right? That's the magnitude of the angle. So I'm in a position to come up with the full x, delta x, which is that x prime minus x is what? Notice that this delta x is in the plane orthogonal to n. If you are really making a rigid rotation, keeping this angle fixed around there. So that's the delta x. Delta theta is there, of course. That's the angle. Now, finite, this is the infinitesimal angle. And cross x. That's the cross, that's the x. In order not to mix my notation of x with the cross, the wedge product, I put a little circle. That's my invention. It doesn't have anything to do, not to get confused with the x's and cross products. That's what I get. This delta x now, the vector, this vector, in terms of the x and the n and the angle, is given as such. So as a result of the infinitesimal rotation, x becomes this, as is clear from that picture. Okay. How do I write the components in general? Let me write the components in general. xi prime, xi plus delta theta, epsilon I j k, nj xk, right? Infinitesimal. Notice that these are all infinitesimal. So if you want, put inf and inf, not to get confused with the full finite rotations. How to go from here to full finite rotation? You have to integrate, but I'm not going to do it for the space. I will do it when I go to the internal ket space or the spin space eventually. So, because working out with the epsilon ijk and converting into a two-dimensional matrix is not that trivial. I don't want to lose time in that. How do I write it in such a matrix form so that I can establish the contact with that? Let me use the following notation. Now let me write this as using the delta ik xk notation. Then it becomes delta ik, sum over repeated indices are always understood. There is no point of repeating it 1,000 times. Delta ik plus delta theta, epsilon ijk and j xk, correct? So this one is the R-I-J matrix as there for the infinitesimal case, right? Sorry, ik. Indeed, xi prime is rk times xk, sum over k is understood. So that's my rotation matrix written in terms of the Cartesian coordinates. So you see, it wasn't that difficult actually to work it out, because in certain books, to simplify life, they go to z-axis and polar coordinates, etc. Let's try to proceed as much as possible with this Cartesian notation, because it is more aesthetical, really. At least that's my personal opinion. It may change from people to people. I will. So what is this? RIK is delta IK, the identity that is. Delta theta, it's proportional to the delta theta. When you let delta theta goes to 0, this goes to identity. That's the infinitesimalness. And epsilon I and epsilon k, the first and the third index is here, the indices, and there is an intermediate index which is contracting the j. So that's a very quite aesthetical, really. You may immediately demonstrate that it satisfies the orthogonality property that we worked out for the full case. It's more or less a trivial example, but let's do it for the heck of it if you want. So what is it? We would like to demonstrate that R transpose and R is I, or sum over I, R.I.K, R.J.K. K is delta ij. That is, putting our dagger if you want, convert it into the index notation. So what we should do is write this and then drop the, in the infinitesimal case, because in the product there will be delta theta squared terms. So what is the direct term? Delta ik times delta jk. Ik times delta jk gives you delta ij. Obviously, the first term is delta ij. And there's a second term. Second terms, cross terms. This with the other, and the first term of the second with this. And obviously, they are anti-symmetric, right? Well, let me write it. Delta theta times delta ik times epsilon j, k, and L in here. Remember, I and k. The first and third index are the indices which appear there, j and k, and there's an intermediate one which brings it here. So this, what about the other term? Delta jk times epsilon I m L and m. Again, the middle, I and L is the I and L is the no, I, K, J, K, and J, K, I, K. Okay. Notice that if you carry out the summation, which summation is it? K summation, this becomes epsilon IMJ times NM. This becomes epsilon J JIK N L JLK JLK N L. Change the L to M, JMK. IMK. Now what am I doing? Now let me do it cleanly. L is there, IK, epsilon J, Li, NL. IJ, now that's safe. JK, so this one is epsilon IML, IMJ, NM. So let's change it to L. Okay. JLI, ILJ. If you put it, put the J all the way back, LIJ, ILJ. Cancelling each other, so it is really. Well, that was too trivial, perhaps. The way it is constructed, it was obvious, but still it's always good to verify that it indeed does the job for us. So let's proceed a little further. I will start again deviating slightly from the book with the ordinary orbital angular momentum to motivate ourselves, and then eventually move to generalized, a generic angular momentum operator, which is identified as the generator of the rotations. Well, we know, let's verify that at least in the ordinary life, the orbital angular momentum is the generator of the rotations in the space, 3 space. Then we can abstract, go to the abstract space and generalize it. So the next is orbital angular momentum. Using correspondence principle, we will carry over from classical region, orbital angular momentum as the generator of space rotations. we will mimic the steps that we have used in working out the generator of the space translations, which was involving the momentum, linear momentum operator here, angular momentum. So what am I going to do? I will first start from the definition of orbital angular momentum. That's the classical definition. When x and p are ordinary dynamical variables, when you replace them with the operators, the x with the x operator and p with the p operator, then you go to the quantum mechanical. I now stick to my old definition saying that when I use operators, I use capital letters and the small letters are associated with their eigenvalues. That's okay. So this is the angular momentum. Well, there's a trivial statement first. We have to demonstrate that it's Hermitian. You may say, of course, you have seen it in your freshman physics. I'm joking, of course. Well, let's show that it is Hermitian rather quickly. How do we do that? When you take the Hermiticity Hermitian conjugate, what you have to do, what you have to do is the following. If you blindly say that you cross the order and put the daggers as P is Hermitian and X is Hermitian, P dagger is P, X dagger is X. So dagger is P cross X. Then as X and P do not commute, then you may say, well, it's not perhaps Hermitian. I'm trying to tease you a little bit, of course. What I'm doing rather quickly doesn't make too much sense. The safest thing is to look at the index. Whenever you have such complicated expressions, look at the index form. Now, it's much better that way, right? Now, you take the Hermitian conjugation and you jump P over X, put it to the left, and you have then, as epsilon I, j, k are real numbers, right? 0, +1, or -1, there's no danger coming from the epsilon. It is pk and xj, and then you jump pk over xj using the basic commutation relations, which were xj and pk are ih bar delta jk. Again, at first you say, if I now, after taking the Hermitian conjugation, p put to the left and x to the right, you jump p over x, there's an additional piece. xj pk minus pk xj is not equal to 0. What does go wrong in here? Comments? Well, there's a delta ij additional piece, right? Epsilon ijk times delta jk. Epsilon ijk is anti-symmetric in jk. Delta jk is symmetric in jk. When you contract all the indices with anti-symmetric and symmetric, you get 0. So that additional piece seemingly there is 0. And indeed, L dagger, Li dagger is Li. Sorry for the simplicity of this example. It's simple, but you have to always keep in mind, these simple things may be sometimes confusing. It's Hermitian, that's nice. It's a very good observable, along with other observables, X and P and Hamiltonian. L is also observable, and they are going to have real eigenvalues, and eventually, when we talk about the eigenvalue problem, these will be quite crucial ingredients. Fine. Once we understood the simple Hermiticity property, let's mimic the steps we have followed in the space translation case. What do I mean? If I'm going to really demonstrate that orbital angular momentum is the generator of the space rotations, then I have to see the effect of this orbital angular momentum operator on what? On the position operator eigenvector, for instance. How does it change? Because remember, position operator eigenvector is this. When we were applying a space translation, and it was moving to this, right? And we have showed that the generator is the momentum, for instance. We have taken the momentum and act on it, and we have shown indeed that it shifts it by that amount. So if I'm going to demonstrate this, I have to see the effect of the orbital angular momentum on the position operator eigenvector basis. Okay. I will proceed in the following manner. What is the effect of L on X? How does it for the general case? Well, instead of the general case, in order to make use of those nice simple pictures, let me choose the LZ component and let's see how the LZ component acts on the X. We know from ordinary classical mechanics that when you make a rotation about the third axis, it mixes the first and second coordinates. Right? Cosine theta minus sine theta, cos theta. If you're in the z-axis and the rotation takes place in a plane perpendicular to the z-axis, x1 and x2 are mixed. x1 prime and x2 prime are functions of x1, x2, and the angles are cosine theta minus sine theta, etc. So it is easy to visually picture that. Therefore, I will use the LZ for this case as well. So what is the LZ or L3? Use the numbering notation. Let's put the operator on X. How does it affect? Okay, let me move to this side and let's do it in here. Now, what is LZ? 1, 2, 3, or L3. L3 is X1, P2, X2, P1. Sorry for this cumbersome notation. I'm trying to emphasize that these are the operators. Okay. Now, what do I need? And X is the position operator eigenvector basis. Therefore, these are defined as xi, x is xi and x. That's the definition of these position operator eigenvector bases. That is, if this is capital X1, this is little x1, capital X2, little x2. That's the definition. This is a common eigenvector of the three component of the position operator. Remember, when we were discussing it, we have spent some time on it, saying that x1 operator, x2 operator, and x2 operator commute. Therefore, they have a common set of eigenvectors. The arrow means x1, x2, x3. Okay. And we have also worked out the effect of the momentum operator on the x. What was it? Px was IH bar. Notice the sign change from the space of functions to the position operator eigenvector basis. That was the expression that we have worked out. Therefore, L3 on X is X1 P2, therefore IH1 X1 d dx2 minus X2 d dx1. Yeah? X. Now I go from capital letter to small letters, because capital X acting on the position eigenvector gives you the eigenvalue, which is little x's. Okay. That's nice. Now to see really what do I have, let me think of the operator in the following form. The infinitesimal, the supposed infinitesimal operator, the operator which carries out the rotation about the third axis. So I denote that as U R3. R is the rotation, 3 is the about the third axis, U is the unitary operator which does the job in the ket space. You see, you carry out a rotation in the classical space and you go to the ket space, quantum mechanical space, and you see the effect of that rotation in that space. That's the reason why I resort to this one. In order to be norm preserving, U's should be unitary, as L is Hermitian. In order to make a unitary operator out of a Hermitian one, I introduce this. And this sort of is the answer. This is a correspondence principle expecting from the classical physics. So we are sort of verifying that it's really the rotation of the it's the generator of the rotation about the third axis. So this is when the infinitesimal case, inf, then it reduces to, my notation is that when it's finite, I use the full letter. When it's infinitesimal, I put the delta on it. That's really rigorous. That's more descriptive than the notation. He put the delta up in the exponential. I don't agree with him. Delta is to be only in the infinitesimal case, so I bring it down. So L3. Obviously, that is, if this is the full form, that's the infinitesimal form. An identity minus a term which depends on delta theta. When you take delta theta goes to 0, it goes to the identity. Obviously, that's really trivial, right? Identity is no rotation case. Infinitesimal case is identity plus a delta theta. So this is a good construction. So what is the effect of this on the x now? I worked it out in detail, so I would like to see what is the effect of this UR3 on the x in the infinitesimal case, inf. Let's put that. Although it's cumbersome, if you would like to feel safe, whenever you are doing infinitesimal case, put the notation inf on it, okay, because it's not full form. So it is I minus I over h bar delta theta L3 on x. Then we worked out L3's effect, so let me put it in here. Copy it from up. What is the L3? Sorry. L3 acting on x gives you IH bar x1 d dx2 minus x2 d dx1 on x, right? That's the effect of L3. So what do I get? Again, in the infinitesimal, UR3 on x infinitesimal case. The first term is the x, because identity times the x, minus I over h bar times IH bar. There's a minus I squared, so it's plus h bars cancel. So I have delta theta x1 d by dx2 minus x2 d by dx1 times x. Let me expand this. What is it? Delta theta x1 d by dx2 x1 minus delta theta x2 d by dx1 x1. There is no third derivative as we were carrying out the expansion, the rotation about the third axis. What is this really? Is this the Taylor series expansion to first order of the following? x1 plus minus. I claim that this right-hand side is the Taylor series expansion of this thing. Why is that so? What do you do? This is a multivariable vector, the first variable, second and third. The third one is not affected because we have chosen that third rotation on purpose. So how do you expand this? This is you expand about the point x1 and x2. This is untouched. There is an infinitesimal change. So it is x1, okay, x2 and x3 plus or minus delta theta d by dx1 of the entire thing, that is x1, x2, and x3, plus delta theta d by dx2, because that is the second term you are expanding about here, times, again, x1, x2, x3, and that's it, because there is no additional term. x3 is untouched. Is this the same as that? Yes, right? Sines. What's wrong with the sines? I've taken it to be minus, and derivative is with plus, minus, and minus became plus. Second is plus, the first is minus. There, the first is plus. No, it's correct. It's correct. Sorry. This one is this, and that one is this. Sorry, it's all the same. Notice that this is with the plus sign, and that's with the minus sign. Exactly. So this expression is nothing but the Taylor series expression of for this one. Therefore, I write this as, now this is equal to inf, of course, x1 minus delta 2x2, x2 plus delta x1, delta theta x1, x3. So this is what it does. This U operator, which is constructed here as such, when it's acting on the position operator eigenvector basis, it changes x1 to this, x2 to that, x1 prime, x2 prime, and x3 because it's untouched. Is this really the rotation I have in the classical case? Let's check it against the rotation theorem that we have worked out, whether it agrees or not. Then if it agrees, then our claim that it is the generator of the rotations would have been demonstrated. Okay, so I'm going to come here and try to check against the picture that we have plotted. So what is the third rotation from here? Rotation about the third axis. That is, n is in the z direction, right? N defines the rotation axis. N is parallel to OZ, and then n cross x is what? Well, let's do some elementary thing. E1, E2, E3, and z is in the third direction, 0, 1. This is x1, x2, and x3. So what do you get? What is this vector like? E1 is minus x2. E2 is with a minus plus x1 and 0. Therefore, x1 prime is inf, I'm reading from here, x1 minus delta 2 x2, and x2 prime is inf x2 plus delta theta x1, and x3 prime is x3. It's not affected. Let's check. Is it the same? x1 prime is x1 minus delta theta x2. x2 prime is x2 plus delta theta x1, and x3 prime is the same. So indeed, L3 is the rotation, generator of the rotation about the third axis. So I can generalize you. I invite you to work on your own. Use this language. This Cartesian language is more appealing, really. So Li, the orbital angular momenta, the components of the angular momenta are the generators of the rotations about the associated axes. That is, L1 is the first axis, L2 is the second axis, L3 is the third axis. Wonderful. Perhaps before proceeding any further, this we have worked out in the on the position operator eigenvectors. You may wish to try those on the space of functions of x. Li on f of xi, for instance. What if you have functions? Why this is relevant? Because these are like the wave functions themselves, right? As we are going to use the wave equations to discuss hydrogen atom, for instance, although we are not going to do it in here, I will comment upon them. So if you have to act by the angular momenta on the wave functions, it is like these. There will be some slight difference, obviously, because remember, the momentum operator, when it acts on the position operator eigenvector basis, it is IH bar times the gradient. But when it acts on the functions of x, it's the minus IH bar, the gradient. You know the reason. Any general vector can be expanded in terms of these basis vectors, right? These are the coordinates, the wave functions. These are the basis vectors, which are the position operator eigenvectors. And the summation, typical. The other day I was checking the notes of the former students of mine. I don't have systematic notes. Sometimes I look at the notebooks of the students. She was making a comment. She said, I didn't understand the connection between the... Well, if you don't understand, please ask. It's simple, right? This is the three-dimensional vector space. This is the sum and the position. I get the basis vectors and coordinates sum together with the dx. If you want to be rigorous, as we are using the full notation, the position operator, the basis vectors, coordinates. So it's really a one-to-one correspondence with this notation. Anyway. So a quick check on the role of Li on Fx is just going to be, the only difference will be the momentum operator on the functions of x will be like minus IH bar times d by dx. But anyway, let's do it. At least let me sketch, instead of spending too much time on it. This is more or less a trivial thing. Let me just, in the remaining few minutes, let me show you how it goes. Okay. Okay, so let me have this minus I over h bar theta L3 again on f of x. Now this time this functions, not the position operator eigenvectors. Again, let's go to the infinitesimal case. I minus I over h bar, identity minus I over h bar, delta theta, if it's infinitesimal, I change the notation to delta theta, L3 on fx. Now this one is what? P on the functions is h bar over I minus I h bar. x1, yes, dy dx2 minus x2 dy dx1. So this goes like f of x minus plus, here's another minus, right? Just delta theta, and x1 d dx2 minus x2 d dx1 f of x. Again, if you want, you can write it as plus delta theta x2 d by dx1 f of x minus delta theta x1 d by dx2 f of x. Now, what do we recognize? We recognize that this is like f of x plus delta 2 x2, x1 plus delta 2 x2, and here okay. There is a seeming paradox in here. I invite you to think of in terms of the passive and active. When I was acting on the position operator eigenvectors, what I was doing was changing the basis vectors. Now I'm changing the vector itself. It may sound puzzling at first, but anyway, it's not. For those careful eyes, x2, delta 2, x1, x3. x1 prime, x2 prime. Remember, the signs are opposite. Because in one case, I was changing the basis vectors, I'm changing the position vectors now. It may be a little confusing, so that's all I would like to comment upon. And I deviate now from here and proceed. After the break. Notice that I have I'm deviating from the book. I have to speed up. If I stick to the book, there will not be enough time to finish the chapter 3. I will finish the chapter 3 by focusing on specific subsections. Okay.